I have been duplicated. Fortunately, deduplication works well. And fortunately, I am the one who stays here, but not the duplicate. Okay, so quite frankly, this talk is dramatically inspired by a blog post written by Frank Pashot, and Frank Pashot is here, and his colleague, Denis Magda. You probably know both. But today, I'm going to have a look on this situation with sharded and distributed systems from a little bit different angle. So my name is Evgenii, or Eugen. I'm developer at YDB. I'm a massive fan of distributed systems, and also I like databases. So it's nice when there is combination of distributed system and database. That's, I think, the best combination. And recently, I have started my presentations from a very important stuff, the most important stuff in this presentation, because there are strong rumors about YDB and Yuga by YDB. Guys, how do you think? Are they the same? Raise your hand who thinks that these systems are the same. Okay, and how many of you think we had? Now I have microphones. It's like good distributed systems, master and two replicas. So it's a good insurance that I will be able to talk. So, and how many of you think that we had a bar fight? Wow, at least one, at least one. It wasn't yesterday. So here is the truth. Here is the truth. YDB and Yuga by YDB are completely different distributed systems developed by different people and by different companies. But we enjoy discussing distributed systems, benchmarking, results of benchmarks in a very friendly manner. So let's go to our topic. And let's discuss database management system types from application perspective. When you start a project, probably you have proof of concept. Usually you start from a very small database. Your data is not available yet. So it's okay to not have replication. But then, when your project becomes mature, you have to use Postgres with proper configuration to keep your data safe. At some point, it may happen that you succeed, and you have many clients, many connections, you have big data, you are a very successful person, but you have a choice to shard your database for your new workload, or to use distributed database management systems. And there are many concerns regarding this choice, and I'm going to speak about these concerns a lot today. So besides performance, there are important things like availability and durability. And both imply replication. And also, we are going to talk about replication a lot. Because when you use replication, it becomes important how you utilize your hardware resources. So, just to sum up. Okay, so it's... Oops. So one moment. So, I'm going to discuss sharding and wide and distributed transactions, and surprisingly two-phase commit, because there are some strong myths and misbeliefs around them. Then I'm going to discuss Citus in terms of wide transactions, because when you use wide transactions, it's not well known, but Citus is not ACID compliant, and you should keep it in mind when you develop your application. And finally, we will discuss performance using TPCC benchmark, comparing Postgres against distributed systems. So, first of all, myths and misconceptions. The idea behind sharding is straightforward. You have monolith, and then you shard it into pieces. And now you have n databases instead of one. You put a special coordinator or routing layer, and now it's end point for your clients. But now you have two types of transactions. You have single shard transactions and multi-shard transactions. In this case, it's visible to clients because there are different guarantees for each type of transaction. And it's important to keep in mind that guarantees are really different. Before we delve into guarantees, let me recall you what is ACID. ACID stands for atomicity, consistency, isolation, durability. And please trust me, all your transactions need is ACID and proper ACID. Isolation levels, there are multiple isolation levels. Serializable is the only correct isolation level in my opinion, because in this, and it's default in SQL standard. Also, it's default in some databases, even distributed ones. For example, in CockroachDB and YDB, it's the default isolation level. And in this case, anomalies are impossible. But there are weaker isolation levels, like repeatable read, or also known as snapshot isolation, read committed, it's default in Postgres, and read uncommitted, which is a very dirty isolation level. And from practical considerations, it's extremely important for application developers to understand the difference. Because when you use serializable level of isolation, it's up to database to provide you ACID properties. But when you use weaker isolation levels, it's up to application developers to think about their transactions, to provide isolation, consistency, and to fix bugs. Because usually if you use weaker isolation levels, there are high chances of having bugs. For example, there are cases when millions of bitcoins were stolen just because of a weak isolation level. So in my humble opinion, everybody should use by default serializable, and if performance starts to matter, it can be relaxed if it doesn't sacrifice consistency. And surprise, Citus is not ACID. White transactions in Citus are not isolated. And okay, however, not everybody needs white transactions. Probably your application uses just single-shot transactions. In this case, you are safe. But if you use white transactions, it might be a problem. Let's look on an example. Suppose you develop banking application, and there are accounts, and you should be able to transfer from one account to another account. It might be accounts of single person or different persons. Also, it's important to be able to calculate total sum, especially between accounts of same person. So you take your cell phone and you look on your balance. Now suppose Alice transfers money from her account to Bob, and simultaneously there is a transaction. Here is repeatable read, so everything is supposed to be okay from application, and it calculates total balance. In Citus and Citus-like solutions, if these accounts are on different shards, balance might be wrong. It might be correct, it might be less, it might be greater. So you see you have more money, it's okay, it's nice. But then you see correct balance. Or you might see that you have insufficient of money, which is also not nice. And also people claim that this example is wrong, but it's correct, because there is two-phase commit. And two-phase commit is supposed to help to do transactions. And it's a very common misbelief, because two-phase commit is just about atomic commit. It means that either all parts of transaction are applied, or none of transaction parts applied. So it's like abortability. That is why many researchers and practitioners suggest to call this feature not atomicity, but abortability, because it sounds maybe worse, but it's better to understand what it really means. And two-phase commit achieves abortability. It's a character in ACID, but it's not it's not isolation. So two-phase commit doesn't implement distributed transactions at all. And let's look on sharding in distributed database. In this case, shard is implementation detail for applications, because there is no difference between white transactions and regular and single shard transactions. It's completely invisible to end clients, so it's easier here. But why do people do things like Citus? Are white transactions really that expensive? Well, in theory, people to calculate transaction execution time, they typically express this time in number of RTTs, round trip time. And usually I/O is negligible because you have NVMe disks, but in case of HDDs, it's also in this example, it's kind of negligible. In Postgres, transactions take 1 RTT because you have to use replication if your data matters. When you use sharded Postgres, it takes 3 RTT because you get also two-phase commit. So you have 1 RTT for replication, and you have 2 RTTs for two-phase commit. In distributed systems, it's even greater. Here as example, I use YDB. At least this example is chosen because my t-shirt, to match my t-shirt. In case of YDB, it's 4.5 RTTs and some small constant for playing and batching. But let's build a graph of dependency of transaction time in milliseconds from RTT. You see that on the left, the difference is almost negligible. And it's 500 microseconds. It's a huge ping if everything is located within single availability zone or nearby. Even when you have ping 7 milliseconds, the difference is not that dramatical. As you see, the difference between replicate sharded Postgres and distributed system may be around 10 milliseconds. And still, distributed transaction is below 50 milliseconds, which is enough for most of your applications. So, in a multi-region cluster, the difference can be really significant. In this case, sharding might work better, but if you don't need consistent global snapshot. I talk a lot about replication, so it's time to do some Star Wars stuff now and discuss replication in depth. First of all, there is important concern how many standby replicas is enough for your application. I think that 3 replicas is a good minimum number. Maybe that is why 3 is everywhere in religion, in replication, almost everywhere. So you have to use leader and 2 standby replicas. That's a good number because in this case you tolerate single server failure. And also you should consider what you would like to use, async or sync replication. But I think that async replication without synchronous replication is a crime. And usually people who use async replication without sync replication, they are finally punished because they lose their data. Also, if you use async replication, there are chances of data loss, stale reads, and anomalies. The only proper use of async replication usually is a combination of sync replication and async replication, at least if you use standby replicas. So there is another concern, it's resource utilization in replicas. Because if you want to have everything consistent, you will do all your transactions through the leader, and replicas will be idle. So suppose your leader consumes X CPU cores. In this case, you have 3 X cores in total because you have 2 replicas. Also, you would like to tolerate single server failure. And so you should rely on at most 2 servers working simultaneously. If you could utilize replicas, you can use half of original cores, because now you split the load between 2 servers, not just 1. It's cheaper because you can use servers are cheaper with half of cores, and also you require less memory. Same time, this allows usually to reduce latency. So with 2 replicas, idle time is 66.6%. It's an enormous number. It's as bad as utilization 99.9. It's okay if your server is small. 16 cores, it's cheap. But your server might have 128 cores, or maybe even more. It can be 300 cores, a lot of NVMe disks, and it's really a waste of money to have replicas doing nothing. In sharded systems and in distributed systems, everything is better in this aspect, because you can spread replicas and leaders among all hosts, and finally you get twice better utilization of hardware resources, still because you should tolerate 1 server failure. Besides that, as I will show you later, there is architectural problem with replication. It's single-threaded in Postgres. But if you have many shards, now you have small replication threads, not busy ones, and it scales better. So you should, from what I have said, you should remember that Citus works great with single-shard transactions, but if you use multi-shard transactions, you might be in trouble. And that makes Citus not Postgres. It's very easy to install Citus, but you finally get completely different database with different guarantees. So Citus is not distributed database management system, and if you need wide transactions and consistent global snapshot, don't be afraid to use distributed systems like Yuga YDB, CockroachDB, or YDB, because as I have shown, in many cases, distributed transactions are not that expensive as people usually believe, because we have a really fast networks. But it's not the end. We have another part, and there is important question: when Postgres is not enough, because Postgres is a very efficient database, and it's unclear when it might be not enough. And to answer this question, we took TPCC benchmark. It's a very popular OLTP benchmark. 3 powerful servers. Servers are powerful because we want to check vertical scalability of Postgres to give it chance. And we took distributed databases and set up and use them in the same hardware installation. And let me slightly recall you what TPCC is. TPCC is ancient stuff. It has appeared in 1992. I think I was just 3 years old. Maybe some of you were not born yet, but TPCC was already. Dinosaurs already died, but not too far from TPCC creation. And there were no Tesla, no Android, no SpaceX, nothing we are used to nowadays. So the world was very different, and TPCC already exists. And Yuga YDB, TIDB, CockroachDB, YDB, everybody agrees that TPCC is the only objective comparison for evaluating OLTP performance. Also, I absolutely agree with this because it's a great benchmark. It's well designed. It's very simple. There is a company. It simulates, a benchmark simulates e-commerce organization. There are warehouses, and warehouses trade goods. And transaction logic of TPC transactions is easy. You specify number of warehouses as a start parameter. Depending on a number of warehouses, you can increase or reduce the load. Each warehouse is about 100 megabytes of data, and it serves 10 districts. In each district, there is a terminal, like in real life, and customers use terminal to create new orders, to make payments. Warehouse workers use terminal to make delivery, and from time to time, like in every warehouse, you have to make an authorization. So most of transactions are new order and payment, and minority of transactions are order status, delivery, and stock level. You might be surprised that delivery is just 4%. It's because delivery is batched also as in real life. TPC transactions are nice because they require a reliable level of isolation in case of Postgres because of how they have implemented repeatable read. In Postgres, it can be repeatable read. They are multi-step or interactive, so it's also useful to test this kind of stuff. They have twice more reads than writes, and they use TPMC as integral metric. It's a number of new order transactions per minute. So it's integral metric. And the most well-known implementation of TPCC is done by Bench-based project at Carnegie Mellon University under Andy Pavlov's supervision. It's a very beautiful multi-DBMS SQL benchmarking framework based on JDBC. It's done in a way that it's very easy to add new databases, and it's very easy to add new benchmarks. So Yugabyte uses fork of Benchbase, and we decided that we have so many similarities in our naming, so we can fork Benchbase too. And we did it. But slightly after, we have discovered that to execute just 15,000 warehouses, it's 1.5 terabytes of data. On client side, on benchmark side, we need 150K operating system threads. That's crazy. It doesn't work well. Also, it required to use 600 gigabytes of memory. So we ended in a situation when we have 3 servers for database, and we had 5 servers, similar servers for benchmark. And that's kind of crazy. Then we did some math, some calculations of the price. We decided to test scalability of different distributed databases to make this kind of comparison in Amazon. We did calculations, and single run would cost $10,000. And usually it's not enough to do a single run to make proper comparison of databases. So we did some optimizations. The major optimization is a change from operating system threads to Java virtual threads. It wasn't easy because it's not transparent change. Java virtual threads can cause deadlocks. By the way, I forgot to mention, I leave some links on materials, and then there will be QR code with all materials, all the links I leave within the presentation. So we found deadlocks in case of YDB and Postgres. So there are 2 repositories for TPCC of improved TPCC for YDB and for Postgres. But because Benchbase contains a lot of different benchmarks, a lot of different databases, it's really complicated to test Java virtual threads and to find all the deadlocks. So it's complicated to get our changes to upstream. So it's time to tune Postgres. So maybe some of you remember a popular MTV TV show, Pimp My Car. So it's similar we do with Postgres. And tuning Postgres is a lot of fun. Our setup is simple. 3 bare metal servers, single data center, 128 cores, 500 gigabytes of memory, 4 NVMe disks. We use huge pages and relatively old Ubuntu. And our main requirement, database should survive single server failure. That is why Postgres has 2 sync replicas. Cockroach and YDB use replication factor 3. In Postgres, everything is configurable. Write-ahead log, B-tree, execution engine, replication, I/O. Maybe that is why we have a multi-day conference and it's not enough to cover all the topics. And we decided to choose a special approach to tune Postgres. We started from fault-intolerant Postgres with no write-ahead log, no replication, so it's most performant configuration possible. Then we added val, results were not good, and we added huge val. With huge val, I/O distribution was ideal, performance was great, but it's not a production setup because recovery time takes tens of minutes. Then we added replication, replication config number 1, and replication config number 2. The difference is that in second case, we changed disk arrangement. We started to use 2 NVMe disks in RAID 0 for write-ahead log. I will tell you why later. And here are results of TPCC for various configurations. As you see, fault-intolerant configuration of Postgres is extremely performant. It's twice as performant as final fault-tolerant configuration. And as you see, we have achieved some good results between replication config number 1 and replication config number 2. So if your data is not valuable, for example, you can generate it. It's okay to use no val configuration. You get extreme performance. And synchronous replication in Postgres is a bottleneck because there is one thread applying write-ahead log. That is why disk rearrangement helped a lot to increase performance. Also, it's important to keep in mind that synchronous replication limits vertical scalability. So vertical scalability, unfortunately, is limited. It's not enough just to add more cores and more memory in some cases. So there is also a blog post with more details, with more results. You might want to check it later. But is 200K TPMC a lot? It is the result we got for fault-tolerant Postgres. I think it's quite a lot because it contains 130K database queries. It's a huge lot for many applications. Also, as you see, there is a huge hardware consumption. A lot of disks consumes as crazy. The only resource is not consuming a lot is CPU, because Postgres is very efficient. Just 20 cores out of 128. And the last open question is if distributed systems can show comparable results on the same hardware. Because usually when I say distributed system, I suppose something scalable, horizontally scalable with hundreds of servers, and people usually believe that on 3 servers performance would be poor. And we decided to use benchmark to check and actually get some proper numbers. We decided to compare Postgres against YDB, again it's my t-shirt, and CockroachDB. I don't have CockroachDB t-shirts, by the way. But unfortunately, we were not able to compare against YDB for various technical reasons. I hope we will do it later, maybe this year at least, I hope. YDB is open source distributed SQL database. It has partial Postgres compatibility. We have OLTP, OLAP, and Kafka-like topics. And I think that Kafka-like transactions between Kafka-like topics and tables is, I think it's unique feature of YDB. It simplifies life of developers a lot. I mean, application developers. Of course, we are strong, consistent. We have cluster with thousands of servers, open source license. Feel free to start our project on GitHub. So probably that's the end of advertisement. And CockroachDB. Here is maybe kind of anti-advertisement. Unfortunately, they left open source. They are also distributed SQL database. They have a very good performance. They also have partial Postgres compatibility. To the extent of my knowledge, they provide LTP only, and they have strong consistency. And here are results. Okay, again, about my t-shirt. Despite having YDB t-shirt, Postgres wins. That's a rare case in benchmarking. Usually, if you are YDB, YDB wins. If you are CockroachDB, CockroachDB wins. And something wrong with us, because Postgres won. And YDB is slightly worse, has performance slightly worse than Postgres. It's about maybe 5%. And CockroachDB is, I think, 30% away from YDB. We have contacted CockroachDB guys. They have validated configuration. They have validated results. So everything is fair. Results should be clean. But Postgres has some issues with latency. Latency is uneven. So you see there is a good latency, and from time to time there are spikes with a really poor latency. That's happening because each peak corresponds to checkpoint. You start checkpoint and you get bad latency. All database sessions are hanging waiting for sync wrap. Again, I have already told you there is only one thread receiving and applying val, at least applying val, maybe receiving also by replicas. And it's a huge bottleneck. So it's time to conclude my talk. I wish I could speak more. I like speaking, and I like the audience. So Postgres is highly efficient, but unfortunately it doesn't scale horizontally. At some point you have to scale your database, and you have choice, sharded or distributed. And synchronous application limits vertical scaling of Postgres, so this moment when you have to choose comes earlier than you exhibit number of cores. And I would like you to remember that Citus is not ACID compliant. It doesn't provide same guarantees as Postgres for wide transactions. And when you need serializable distributed transactions, please consider distributed database management systems. They are more efficient than commonly believed. I will be glad if you start using YDB, by the way, so feel free to download and to install. Thank you so much for your attention. Thank you for coming to my talk. This is QR code on materials and links. Feel free to ask your questions, and feel free to hit me up during the conference or after conference. Here is my Twitter. Also, it's my LinkedIn. Just drop me a line if you wish. Thank you so much.
For Citus, you mentioned it is not ACID compliant. So if I understand correct, it is true only for transactions which are involving multiple shards, right? Not the single shard. So in case of transaction involving multiple shards, so which ACID property is impacted? I mean, instead of strong consistency, it will become eventual consistency, right? That's what the impact is.
Yes, in case of wide transactions, it's eventually consistent, and it's similar to reading read committed property isolation. It's in the sense it's similar. There is a post with extra information. If you Google Frank Citus ACID, you will find a great post with PG bench examples showing that it's not ACID compliant. More questions, please? If you get any question later, please hit me up. Thank you so much for your attention and for coming.
Thank you, Evgenii. Thank you all. That's why I conclude the talks from the Jupyter. Thank you. Have a nice day.